We saw galaxies as plasma structures, in whose spiral arms huge electric currents flow towards the center. The conditions in galactic plasma can be compared to those in thunderclouds. Different areas of the clouds can take on very different charges, resulting in electrical discharge within the cloud. This results in so-called cloud-to-cloud lightning. In the plasma of a galaxy, exactly the same process takes place, only on a much larger scale and therefore over much longer periods of time. On September 3, 2009, the Herschel Space Observatory captured this image of a plasma nebula in the constellation of the Southern Cross. We witnessed the birth of stars. Of course, in its publication of this image, ESA once again does not speak of plasma, but of cold gas clouds. One should not expect any significant activity in cold gas clouds. But the reality is quite different. ESA states
that a dark, cool area such as this would be bustling with activity was unexpected. But the images reveal a surprising amount of turmoil. The interstellar material is condensing into continuous and interconnected filaments glowing from the light emitted by newborn stars at various stages of development. The result is a view of an incredible network of filamentary structures, and features indicating a chain of near-simultaneous star formation events, glittering like strings of pearls deep in our galaxy.
Obviously, and undoubtedly, we are dealing here with pinched plasma filaments, that is with electric currents. This is a later close-up of the plasma nebula, which, upon further analysis, reveals 27 interconnected filaments. We see a huge, galactic cloud-to-cloud flash several dozens of light-years long. It is in the individual filaments that star birth occurs. In its article, ESA states that these young stellar filaments glitter like pearl necklaces. The breaking up of lightning into separate, glowing plasma balls, that is plasmoids, is a well-known phenomenon during strong thunderstorms. The plasma actually forms a kind of pearl necklace structure. This is a particularly strong form of the Z-pinch effect, which plasma pioneer Willard Harrison Bennett pointed out as early as the 1930s. The process has a lot in common with the so-called sausage instability. In the event of a particular strong discharge, the electromagnetic self-organization causes the filament to be split into discrete plasma lumps. We refer to the resulting plasmoids on Earth as ball lightning and on the galactic scale as stars. Here we see a detailed view of the Carina Nebula. You can clearly see how the plasma filaments are split into individual plasmoids. In this image, we see a stellar jet of matter where the same thing is happening. Stars are therefore not formed by the gravitational collapse of a widely distributed dust cloud, but by the electromagnetic pinch effect. They are produced in galactic lightning discharges and shine in a row like street lamps. And just like street lamps, they rely on the supply of electricity from the outside. In the all-electric model, stars do not shine from within through a hypothetical continuous nuclear fusion that cannot be reproduced in the laboratory. Nuclear reactions may make a good bomb, but they are not useful for highly structured processes such as those observed on the Sun. The thermonuclear model of stars, like the Big Bang theory, emerged in the late 1920s and early 1930s. And just as with the Big Bang theory, electromagnetism was disregarded when modeling the Sun. Nuclear energy had just been discovered and was very much in vogue, while plasma physics, which was in its infancy as well, commanded little attention. So cosmologists tried to explain the behavior of the Sun with thermonuclear reactions, but this caused problems from the very beginning. One of the leading proponents of this model was Arthur Eddington. He wrote in 1926,
"The problem of the source of a star's energy will be considered. By a process of exhaustion, we are driven to conclude that the only possible source of a star's energy is subatomic. Yet it must be confessed that the hypothesis shows little disposition to accommodate itself to the detailed requirements of observation, and a critic might count up a large number of fatal objections."
In the 1970s, leading theoretical physicist Richard Feynman confessed to his students,
"Our equations for the Sun, as a ball of hydrogen gas, describe a Sun without sunspots, without the rice grain structure of the surface, without prominences, without coronas."
This situation has not changed to this day. The thermonuclear model of stars was born out of sheer embarrassment. In the 1920s, astrophysicists were forced to find an explanation for the radiation of the stars, and they simply reached for the lowest hanging fruit, without having a clue about plasma processes and without taking seriously the observed structure of the sun. Ralph Jurgens, one of the pioneers of the electric model of stars, wrote,
"The modern astrophysical concept that ascribes the sun's energy to thermonuclear reactions deep in the solar interior is contradicted by nearly every observable aspect of the sun."
What is being done today in gravitational cosmology is to blame the luminosity of the sun on hypothetical nuclear processes, and to explain away all other properties of the sun that absolutely do not fit into the nuclear fusion model with all kinds of bent ad hoc assumptions. Now let's take a closer look at the structure of stars to get an idea of how all the observed properties of the sun follow directly from the electric model. It is known from laboratory experiments that in electrified plasma, chemical elements are naturally separated according to their ionization potential. The heavy elements are found near the filament axis, while hydrogen and helium accumulate on the periphery of the filament. This process is called Markland convection. Hannes Alfvén explained,
"Elements with the lowest ionization potential are brought closest to the axis and form concentric hollow cylinders whose radii increase with ionization potential. The drift of ionized matter from the surroundings into the rope means that the rope acts as an ion pump, which evacuates the surroundings. Regions with extremely low densities can be produced in this way."
And Göran Markland, after whom the Markland convection is named, explained,
During this convection inwards, the different chemical constituents of the plasma, each having its specific ionization potential, enter into a progressively cooler region. The plasma constituents will recombine and become neutral, and thus no longer under the influence of the electromagnetic forcing. The ionization potentials will thus determine where the different species will be deposited, or stopped in their motion.
The process of Markland convection in a plasma gives us clues about the most likely structure of stars. In their upper atmospheres we find a lot of hydrogen and helium, which led to the misconception that stars must consist entirely of hydrogen and helium. Plasma physics suggests that there is an increase in oxygen and nitrogen in the lower atmosphere. Underneath, we might encounter a solid or liquid core made of heavy elements such as silicon, magnesium, and iron. It is therefore possible that stars have a very similar structure to that of planets. The difference to planets, apart from their size, is simply that stars play a central role in the galaxy's electrical grid. Stars like our Sun behave like anodes, that is, like positively charged electrodes within a plasma discharge process. We may draw analogies to the typical plasma glow in a vacuum tube. The different regions that can be identified in the laboratory can be used to understand the possible structure of the solar supersystem. The Sun, as just mentioned, acts as an anode. The galactic plasma outside the Sun's environment represents the cathode. In the region of the cathode, we see the cathode glow and the negative glow light, which are separated by dark spaces. This whole area corresponds to the heliopause in the solar system. Of course, due to the overall low current density in the solar system, the individual regions do not glow. Unfortunately, the structure of the heliopause is not understood well enough to go into detail here, but the latest data from the Voyager probes, which are now inside the heliopause, show that there are much more complex structures than one would expect in gravitational cosmology. According to mainstream astrophysicists, the solar wind should simply hit the galactic plasma mechanically and form an undifferentiated impact zone. But as NASA announced in June 2011, highly complex, cell-like structures are found, which once again highlight the confused state of current astrophysics.
The Voyager probes appear to have entered a strange realm of frothy magnetic bubbles. This is very surprising. We never expected to find such a foam at the edge of the solar system, but there it is. We are still trying to wrap our minds around the implications of these findings.
In complete helplessness, they quickly reached for the irrationally reified magnetic field lines of the Sun, which are supposed to deform and thus create the cell structure. But magnetic field lines are only representational aids, symbols, not real physical objects. A similar cell-like structure is, in fact, known to every plasma physicist. Charged bodies in a plasma form a protective envelope around themselves, kind of similar to a living cell wall. Such a plasma cell wall is called a Langmuir plasma sheath after its discoverer, Irving Langmuir. Today, the term double layer has also become commonplace. Such a plasma double layer contains virtually the entire charge difference between the charged object and the surrounding plasma. Hannes Alfvén, who was the first to recognize the astrophysical significance of these phenomena, was of the opinion that plasma double layers should be classified as independent astronomical objects.
A double layer is a structure in a plasma consisting of two parallel layers of opposite electrical charge. The sheets of charge, which are not necessarily planar, produce localized excursions of electric potential, resulting in a relatively strong electric field between the layers and weaker but more extensive compensating fields outside, which restore the global potential. Ions and electrons within the double layer are accelerated, decelerated, or deflected by the electric field, depending on their direction of motion. Electrostatic double layers are especially common in current-carrying plasmas.
What the Voyager probes measure today are the double layers in the region separating the plasma of the solar system from the galactic plasma. Since gravitational cosmologists don't know the right words for plasma phenomena, they resort to somewhat childish comparisons with magnetic bubbles and foam. Double layers are not only found as sheaths around charged objects, that is current-free double layers. They form particularly frequently in current-carrying plasmas, as already mentioned in the Wikipedia article. They are often associated with strong Z-pinches, in which stars are also formed. Here we see that the strong Z-pinch results in a kind of hourglass structure in the plasma. This image shows the electric nature of the stars, perhaps better than any other. We see filamentary sheath currents, the star formed in the center of the pinch, and polar double layers. These are not shock waves, as assumed in gravitational cosmology, but self-luminous plasma double layers separating the positively charged star from the negatively charged galactic plasma. Double layers can remain stable for long periods of time, but they can also explode under certain conditions, for example when the current density suddenly increases. Some of the most impressive plasma nebulae may result from such an electric explosion. In a vacuum tube, the Faraday space is followed by the positive column. This is the area where the planets are located. The so-called solar wind, which in reality is not a neutral wind but a plasma, also does not glow due to the low current density. The positive column is characterized by the fact that it is almost electrically neutral. There are about the same number of electrons and positive ions. The electric field strength is therefore very low, but not zero. In the region of anode glow, the behavior of solar plasma becomes very complex. The corona is the region where the solar plasma begins to glow. It shows the typical filamentary structure of Birkeland currents, which we also know from the northern lights. In fact, the Sun is almost completely surrounded by very strong, global northern lights. If there is no well-defined cathode and an electrical discharge in a plasma, if electrons instead drift to the anode from all directions, as is the case with this wire, for example, then it is called a coronal discharge. That is exactly what the solar corona is. It clearly shows that the glow of the Sun is an electrical phenomenon with a current coming from the outside. The galactic electrons, which previously drifted slowly in the positive column, are now accelerated more strongly towards the Sun. At the same time, the positive ions of the solar wind are driven in the opposite direction. A mystery of standard cosmology is still why the speed of the solar wind steadily increases on its journey. In the electric model, the answer is very simple. The weak electric field in the region of the positive column ensures that the ions of the solar wind are continuously accelerated. We do the same thing in terrestrial particle accelerators. If the Sun were not an electric object, we would certainly not observe an accelerated solar wind or corona. As we get closer to the Sun, we get into the region of the chromosphere. It is the actual anode glow. Alvain hypothesized that double layers at the solar level were responsible for the formation of prominences. The enormous temperature increase from the chromosphere to the corona is a clear indication of the presence of double layers. Double layers hinder the current flow in a plasma, as can be guessed from these images of a stellar jet, for instance. A double layer can be compared to a mechanical circuit breaker, as we see it here. When it is opened, an impressive arc discharge occurs. On the Sun, we constantly see such arc discharges, which here follow secondary magnetic fields. When the double layers involved become unstable, they explode, ejecting large amounts of plasma outwards. Cosmic plasma double layers are also important in other contexts. They can produce all kinds of radiation, from radio waves to gamma rays. They function like particle accelerators due to their strong internal electric field. From the chromosphere, we descend to the visible surface of the Sun, the photosphere. Here we encounter what Richard Feynman called the highly ordered rice grain structure. And as Feynman also acknowledged, this observation has no place in the Sun's thermonuclear model. If it were true, we should simply expect turbulent convection, similar to boiling water on a stove. In the all-electric model, the situation is quite different. The granular structure of the photosphere shows all the characteristics of a secondary plasma phenomenon. Since the actual surface of the Sun is apparently not large enough to process the electrical input of the galaxy through a simple glow discharge in the chromosphere, a secondary, tufted plasma is formed, still high in the solar atmosphere. These anode tufts or granules take on the form of winding filaments that we are now so familiar with. We can get a glimpse of the helical structure in images like this. The formation of such a secondary discharge structure has a very beneficial consequence for our survival. On its journey through the galactic plasma, the Sun inevitably enters regions of different current densities. Actually, its luminosity should vary greatly as a result. And this is indeed the case in the X-ray region of solar spectrum. Here we see the production of X-rays over a period of 4 years. Sometimes the Sun is almost completely dark, sometimes brightly illuminated. The luminosity in the visible spectrum, which is so important to us, does not vary nearly as much. If we take a look at the electrical potential of the positive ions leaving the Sun's surface, we can see the reason for this. The photosphere acts as a barrier that must first be overcome by the ions from the Sun's interior. You can think of this as a dam. The amount of incoming water can vary, but the sluice gates only allow a fairly constant amount to escape. After the ions have overcome this barrier, they roll down the chromospheric slope, so to speak. They are accelerated, which leads to turbulence in the corona. We measure this turbulence as an extremely high temperature. Another observation of the photosphere has to do with the light it emits. With today's methods, up to 50,000 absorption lines can be detected in the solar spectrum. A total of 68 of the 92 naturally occurring elements on Earth can be found in the photosphere. This does not correspond to the predictions of the Standard Model. Where do all the heavy elements of the photosphere come from? In the all-electrical model, it can be assumed that the elements are synthesized on the spot, during strong electrical discharges. We have already recreated such electrical nuclear fusions in the so-called Z machine here on Earth. In the much more extreme environment of the Sun's atmosphere, nucleosynthesis could take place continuously. Another observation that cannot be adequately explained in the thermonuclear model is sunspots. The anode tufts of the photosphere disappear and we can see deeper into the Sun. Contrary to the thermonuclear model, we measure a lower temperature here than in the outer region of the photosphere, which directly indicates that the energy that drives the Sun does not come from the inside, but from the outside. By far the hottest area is the corona, with temperatures of up to 2 million degrees. The electric model offers the following as a possible explanation for the sunspots. Around the Sun, there is a donut-shaped plasmoid. Such plasmoids store electrical energy, which they then release at periodic intervals. Christian Birkeland was able to create similar sunspots more than 100 years ago in his Turilla experiments. If we invert the blue graph, we see that the photosphere acts like a tub or trap for electrons. Electric currents from the plasmoid punch a hole through the photosphere by filling this tub, causing the tufts to disappear and creating an increased flow of energy. This is why sunspots shine particularly brightly in the ultraviolet, even though they appear darker in visible light. Every single solar phenomenon can be explained by assuming that the Sun acts as an anode in a galactic discharge process. The model of the electric sun can be extended to all stars. This is the Hertzsprung-Russell diagram, which categorizes stars based on their temperature and brightness. It is based on real observations, so any model of stars must be able to explain this diagram. The x-axis is inverted in the usual representation. The temperature decreases to the right. If we correct this, we get a diagram that is very similar to this plasma diagram we have seen before. Since stars like our Sun can be understood as positively charged plasma spheres in a galactic discharge process, the similarity of the two diagrams is neither coincidental nor surprising. The size, density, and degree of ionization of stars can vary, as can the electrical input from the galaxy. This results in all kinds of luminous states of plasma. From the only weakly electrified, barely glowing brown dwarfs, to medium-class stars like our Sun, which form a luminous, secondary plasma layer due to stronger electrification, to extremely strongly electrified giant stars that shine in the blue-white light of an electric arc discharge. Such blue giants are mainly found around the center of the spiral arms of our galaxy, where the electric currents are strongest. The tripartite division with sharp separations in the Hertzsprung-Russell diagram could then very well have to do with the known discontinuities of a plasma discharge at an anode. The individual luminous states do not transition smoothly into each other. The typical glow discharge increases to a certain, individually defined point. After this point is exceeded, the nature of the luminous phenomenon changes abruptly. The Hertzsprung-Russell diagram shows these discontinuities quite clearly. At one end we find the brown dwarf stars, which probably differ from large gas planets only in the strength of the electrical input to which they are exposed. In the thermonuclear model, there is a clear minimum size that stars must reach, so that the nuclear fire can ignite in them. Accordingly, we should see a clear separation between large gas planets and small stars. But for years, more and more stars have been found that are not much larger than Jupiter, and yet glow faintly. Just recently, a brown dwarf was found glowing at room temperature. The transitions between planets and stars are absolutely fluid, which is another nail in the coffin of the thermonuclear model, but fits beautifully into the electrical picture. Brown dwarfs glow in a faint reddish light, while gas planets such as Jupiter or Saturn are in so-called dark mode. Here, the electrical input is not sufficient to produce visible light. We only receive radio waves. This is what Saturn's faint electrical hum sounds like. Another mystery of modern gravitational cosmology is that stars change their size rapidly. In the electrical model, this is simply due to the fact that the expansion of the visible glow discharge depends on the electrical input. When a star cannot cope with the amount of galactic electrons flowing towards it with a simple glow discharge, the secondary plasma layer, which we call the photosphere, is formed. It can dynamically expand or contract depending on the current density. So when stars vary in size, it's really only the plasma discharge in their atmosphere that varies, not the entire star. Huge red giant stars are therefore not necessarily compact objects. Their photosphere could simply be at a relatively large distance from the rest of the star. It even seems possible that planets could orbit within the photosphere of a red giant. The expansion of the photosphere cannot continue arbitrarily with increasing current density. At a certain point, the star begins to go into arc mode, shining extremely hot and bright. If the current density continues to be too high for the star, an explosive fission, a so-called nova, can occur. In this process, the star might split so that two smaller ones are formed, which together have a larger surface area than their predecessor and thus cope better with the electrical input. This could be the reason why we see so many binary star systems. Of our 100 brightest neighboring star systems, 40 are binary, 15 triple, and 5 quadruple star systems. It could also be the reason why we discover so many large gas planets orbiting very close to their star. Here, the electrical input after the fission was no longer sufficient to transform the gas planet into a brown dwarf star. So we can see that in the all-electric model, we should expect a large variability in the appearance of stars, which is actually observed. Many very variable stars do not behave at all in the way that the uniformly running thermonuclear model would like. One of the biggest problems in gravitational cosmology has to do with stars that change their brightness at ultra-short intervals. These rapidly blinking stars are called pulsars. In order to be able to explain their extreme variability in the standard model, one must assign magical properties to these stars. Similar to lighthouses, they are supposed to emit focused beams of light and rotate at an insanely fast pace. If such a beam of light happens to point towards the Earth, we see it as a periodic flash. However, pulsars were quickly found to light up several times per second. The pulsar in the Crab Nebula, for example, flashes 30 times per second, and other pulsars have been found flashing over 1,000 times per second. No normal star can spin that fast without flying apart. But instead of questioning the thermonuclear model of stars, neutron stars were simply invented. They are said to be old stars that have shrunk to a few kilometers in diameter, with protons and electrons said to have been compressed into neutrons. These neutron stars supposedly spin as fast as dentists' drills, and at a mass that is said to be many times that of the Sun. Just as black holes were merely used to explain the apparent energy output of supposedly extremely distant quasars, and just as dark matter was invented merely to explain the rotation and formation of galaxies, neutron stars were now invented to explain highly variable stars. It is known from terrestrial laboratory experiments that neutrons cannot be stably assembled without protons. Above a ratio of about 1.5 neutrons to 1 proton, the atomic nucleus becomes unstable and excess neutrons decay into protons and electrons. Nevertheless, cosmologists continue to speak of neutron stars, which are supposed to consist entirely of so-called neutronium, and thus are in direct conflict with all laboratory experience. All because astrophysicists needed a material that can survive the supposed rotational speeds of pulsars without flying apart. The electric model of stars does not need any non-physical inventions to explain the high variability of pulsars. For decades, electrical engineers have been building so-called relaxation oscillators, which exhibit exactly the same type of pulses that are observed in pulsars. A relaxation oscillator is easily built. It consists of a power source that is provided on the cosmic stage by galactic Birkeland currents. It charges a capacitor, which is formed in space by the plasma sheath of a star. Here, the electrical energy is stored until it is suddenly released at certain intervals. A kind of periodic lightning discharge occurs. These stellar discharges in extremely short periods of time indicate that the star is under great electrical stress. The presence of a second star, intruding into the system, can cause such stress. And indeed, with improved observational methods, more and more close companions of pulsars are being discovered. So we don't need non-physical inventions like neutronium and insanely fast-rotating tiny stars to explain pulsars. The oscillations of one or two stars under strong electrical stress lead to pulses that are exactly similar in shape to those of a relaxation oscillator, where the thermonuclear model with its neutronium requires a new physics. Against all experimental results, the all-electric cosmology can simply fall back on well-known electrical phenomena. There are therefore many indications that stars are supplied with energy from outside by galactic Birkeland currents. All their properties can be reproduced in terrestrial plasma experiments without the need to invent any fantastic mechanisms. At the end of our consideration of electric stars, we must realize that we cannot say anything about the age or near future of our Sun. We are dealing with a variable plasma discharge, the nature of which depends on the electrical input of the galaxy. If this should change, which can happen quite suddenly, the position of the affected star in the Hertzsprung-Russell diagram will change rapidly. This was the case, for example, with the supergiant FG Sagitti, about 8,000 light-years away, which in 1955 still shone in the blue light of an arc discharge, but then expanded until 1991 and became redder at the same time. The future of our Sun is nowhere near as certain as gravitational cosmology likes to claim. Changes in current density and exploding double layers are uncertainties that we have to live with. But there is no need to panic. We're in an area of the Hertzsprung-Russell diagram where we have a little bit of room up and down. In addition, the four gas planets shoulder part of the galactic input. And the stars, which pass in front of us on the same Birkeland streams, do not show any abnormalities. Nevertheless, it is true that we are not in such a comfortable situation as gravitational cosmology suggests when it assumes that the Sun will shine unchanged for another 4 billion years. This is wishful thinking. The Sun, like any star, is variable and dependent on the electrical input of the galaxy. Ralph Jurgens was probably right when he said,
We might live immersed in a cosmic discharge and know nothing of its existence.
The new perspectives that this will open up for the future and past of our solar system will be fascinating.